Can anybody tell me what we are up to? Does anybody remember what we're doing?
It's diagonalization.
Diagonalization? Yeah. So that's the title of the chapter, of the section. Diagonalization. So, and we started off with a theorem that said, what does anybody remember the statement of the last theorem? What's the last thing that we did?
Just to finish.
Go ahead, what?
If there are distinct values, eigenvalues for A with the vectors corresponding to the eigenvalues are linearly independent.
Right. So you have it's a matrix, okay, not the important part, but if you have a bunch of distinct eigenvalues, if these guys are distinct eigenvalues with V1 VK, the corresponding eigenvectors. Oops. Eigenvectors. Then these guys, V1 and VK, are linearly independent. These guys are linearly independent, right? So eigenvectors corresponding to distinct eigenvalues are linearly independent, and we have the corollary, which was that thus, if a matrix has, if an n by n matrix has n distinct eigenvalues, we see that there exists an eigenvector basis, eigenvector basis for our n. What happens to Nico? Nico was here just a second ago, and he is gone. Okay, right, because you would have your n distinct eigenvalues. Each one would have an eigenvector associated with it, and so you would have n linearly independent eigenvectors. Well, that'd be an eigenvector basis. Okay, everybody all right with that? This is stuff we wrote down last time. You don't have to write it again, I think. Everybody all right? Okay, this is where we finished up last time. Okay, and so what's good? What's good about having an eigenvector basis? What's good about having an eigenvector basis? So I asked this in the other class already. We already talked about this in the second section, so you guys don't say anything, please. What's good about having an eigenvector basis? Why do we like having an eigenvector basis? Does anybody remember? We actually talked about this before at some point. Like, oh, if we had an eigenvector basis, then such and such a thing would happen. Anybody remember? Anybody? Okay, I'm not gonna answer that. I'm gonna go on to the next. We'll go on to the next. We'll see why it's good to have an eigenvector basis. We'll go backwards to this. Okay. Okay. Does here's the definition. Again, you have an n by n matrix. If there exists an invertible matrix X such that X inverse AX is diagonal, we say that A is diagonalizable. Sometimes people write diagonable. Diagonalizable, or you say diagonalized by X. Okay, so we've seen this sort of thing before, right? You take the, what's called the conjugate, you have a matrix, and then you conjugate it by some other matrix, right? These guys are similar matrices, right? So this is what this is saying, is that if there is some matrix, if you have a matrix and it's similar to a diagonal matrix, then we say it's diagonalizable. Okay, you've got a bunch of invertible matrices, you look at, possible conjugates, maybe one of them is diagonal, then you're diagonalizable. And here's the theorem that will answer the question. A matrix is diagonalizable if and only if A has an eigenvector basis. Well, A has n linearly independent eigenvectors. In other words, if and only if there exists an eigenvector basis of R. Okay, so this will be what's good about having an eigenvector basis, right? You have an eigenvector basis if and only if you are you're diagonalizable if and only if you have an eigenvector basis. So in particular, corollary. Thus, if all the eigenvalues are distinct, if all your eigenvalues are distinct, well then, you're going to have n different eigenvalues. Right? You have n different eigenvalues, and then you have n linearly independent eigenvectors, and so you have an eigenvector basis, and then you'll be diagonalizable. Okay, so if all your eigenvalues are distinct, then all eigenvalues of the matrix are distinct, then A is diagonalizable. Okay, so let's do the proof of the theorem. We'll do the backwards direction first. So suppose that A has n linearly independent eigenvectors. So suppose there exists a basis D1 through Dn of eigenvectors. Okay. we let X be the matrix where we take the BI's as the columns. BI. Okay, now let's consider AX. What's AX? What's AX? If we multiply this guy on the left by A, what happens to it? So let's say that these eigenvectors with eigenvalues lambda 1 through lambda n. What happens when you multiply x on the left by A? Anybody tell me? When you left multiply by some matrix, well, the multiplication occurs. Even if you don't know the answer, you can probably guess what's going to happen. Right? What's going to happen? I'm going to make it right here.
Lambda 1 v1.
Yeah, right. So left multiplication occurs column-wise, right? So we get AB1, AB2, ABN. Yeah, we
But
go.
alpha, when you hit a eigenvector with a matrix, doesn't that not change its doesn't that not change its value?
So what's an eigenvector? It's something that gets scaled when you hit it with the matrix,
Oh,
right? So what's going to happen is that each of these guys, when hit with the matrix, just becomes a multiple of itself. Okay. So it's going to be like this: lambda 1 v1, lambda 2 v2. Right? The new row is going to be just the old row multiplied by the eigenvalue. Okay, so now comes a little bit more matrix multiplication, like testing your understanding of matrix multiplication. This is actually the same thing as this. This thing, lambda 1 v1, lambda 2 v2, dot dot dot, lambda n vn, is the same thing as the B matrix. So the matrix of the BI's multiplied by this diagonal matrix. Right? You see what happens, right? If you multiply it, right, the first entries are going to get multiplied by lambda 1, the second entries by lambda 2, etc., etc. The second column's entries by lambda 2, and so on and so forth. Okay. Everybody all right? Okay. So what do you see? Well, this is x, right? This is x multiplied by, let's call this thing b. Let's call this matrix b for diagonal, right? It's x times d. So ax equals xd. And what you see is that x inverse ax equals d. Okay. Right. So whenever you have a basis of eigenvectors, you can find a matrix that diagonalizes your matrix. You can find another matrix, this X matrix, that takes your matrix and then turns it into a diagonal matrix by conjugation. Everybody all right? Any questions? Still, question? No? Okay. Okay, let's do the opposite direction. Suppose you have that. Well, first let me ask you, how did I know that this b was invertible? How did I know that this x was invertible? This is a review. Why is this x invertible? Russ?
Because B1 should be independent, like linearly independent.
Right, exactly. These are linearly independent columns, right? So it's an invertible matrix. That was one of the things we saw was equivalent to invertibility, right? But the linearly independent columns. Okay, now let's go backwards. Suppose you have that, suppose there exists an invertible x such that x inverse ax equals d some diagonal matrix. So suppose you have that this is true, and you want to now we want to see that we can make up independent eigenvectors. Right? We want to see that there are n linearly independent eigenvectors. Right? So you say, okay, well, we know ax equals xd. We basically run the same thing backwards. We run the argument backwards. We say, well, look, ax equals xd, and so that tells us that a times the columns of x equals, for the same reasons, let's say that d is like this, d1, dn. dnxn. Okay. But for exactly the same reasons, multiplying on the left is just you multiply the columns by the matrix, and so you get this is ax1, ax2, axn equals d1x1, dnxn. Right? But that tells you that these xi's are eigenvectors. Thus, the xi are eigenvectors of A with eigenvalues d1 through dn, respectively. Okay, and so you have an eigenvector basis, right? Because these guys were all linearly independent since the matrix was invertible. Okay. Okay. Any questions about that? Any questions about that? Any questions? No? No? Okay. Okay. So let me make a comment, which is that we actually knew this already. We actually knew this already. And this is what we talked about in the other section, right? If you have if B1 to Bn is a basis of eigenvectors with eigenvalues lambda 1 to lambda n. Think about the matrix representation. Okay, we actually, if you remember what we did in the matrix back in chapter 4, then actually you should have been saying, like, why do we even do this? We already know this. We already know this. You should have been saying in your heads, we already know this. What's he doing? We actually know this already. So think like this. You've got your matrix A. It goes from Rn to Rn. Right? Maybe I should call it T sub A because we're thinking of it as a linear transformation, multiplying on the left by A, whatever. Okay. We tend to conflate A and T sub A. Anyway, T sub A. Okay. Now we've got our basis B, right? So we use that basis B on both sides, right? We use that basis B on both sides, and we get the matrix representation with respect to the B and B bases. Okay, let's call that thing A prime. I know we called it A, but we already used A, so we'll call it A prime. Okay, what is A? What is A prime? What's the matrix representation of this thing with respect to the B and B bases? You remember how you get the matrix representation? How do you get the matrix representation? A prime is the matrix with columns. What are the columns? You guys remember the columns? Or have you purged your minds of the knowledge after the exam? I always did, so maybe you have also. Right? How do you? Anybody remember how to get that? You take the elements of your basis, right? So you remember these guys are B1, Bn. You take the elements of your basis, you map them over, then you take the coordinate vector with respect to that basis, right? So with columns Bi hit with A, coordinate vector with respect to B, right? With columns this, right? This is the ith column. Okay, but what's ABI? What's ABI? Lambda IBI, right? Lambda IBI. Oops. Lambda IBI. What's lambda IBI with respect to the B basis? What's the coordinate vector of lambda IBI with respect to the B basis? No. You want a vector. Remember, you're going to get a coordinate vector that is a coefficients telling you how to get this guy from as a linear combination of the BI's. Russ. It'll be lambda I in what place? Right. There's going to be n components here. Right?
In the ith place.
In the ith place, and what do you have in the other places? Zeros. Right? So you got 0, 0, 0, 0, 0, lambda I, 0, 0, 0, 0, 0, 0. Right? Right? Because lambda I bi is 0 b1 plus 0 b2 plus lambda I bi plus 0 bi plus 1, etc. 0 bn. Right? And so the coordinate vector corresponding to it is going to be the standard basis vector bi multiplied by lambda I. Okay? It'll be zeros with lambda I in the ith place. Right? So what's A prime? It's a diagonal matrix, right? With lambdas down the diagonal, with lambda i's down the diagonal. Okay. So, in other words, this guy is lambda 1 and lambda n. Okay. And conversely, right, if you know that, right, so, right, and you think about it, this guy going back is x, and this guy going forwards is x inverse. Okay, so A prime, the diagonal guy, is x followed by A followed by x inverse. Okay, so you actually knew this already, even if you didn't know that you knew it. Okay. 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 Let's see. Okay, just for exercise, here is a matrix, and I say find x such that x inverse ax equals the diagonal matrix. So take 2 minutes and see how far you can get on this. If you know what you're doing, it'll take you 1 minute. Okay, let's actually do this together. Right? So we're looking for, right, we want an eigenvector basis. Right? That's what we want. We want an eigenvector basis. How do we get the eigenvectors? How do we get our eigenvectors? How do you get your eigenvectors? Anybody? Anybody remember? How do you get your eigenvalues, say?
Well, you get your, the characteristic polynomial.
Exactly. Okay. So first you need the characteristic polynomial. So you say, okay, I'm going to take the determinant of a minus lambda I. So the determinant of this. Right? So set this thing equal to 0. Right? I believe, unless I made a mistake this morning, this is lambda minus 1, lambda minus 2 equals 0. And so you get that the eigenvalues are 1 and 2. Okay, so now we just need to find the eigenspaces, right? Lambda 1, I'm sorry, e sub 1 and e sub 2, right? Well, E sub 1 is the null space of A minus I, right? A minus I is 4, 6, negative 2, negative 3, right? And so you reduce that to 2, 3, 0, 0. Right, 2, 3, 0, 0. And you see that the null space is spanned by the vector 3, negative 2. Wait, sorry, 3, 2. Two x 3 negative 2. 3 negative 2. Right? Because 6 minus 6 is 6. Okay, and then you do the same thing over here. A minus 2i, right? Do the same thing. You get what is it? Minus 2, so you get 3, 6, negative 2, negative 4, which is well equivalent to 1, 2, 0, 0. And so you get that the null space is spanned by negative 1, 2, 0. Okay, right, and so you take as your x those eigenvectors. And you take those guys as you take the eigenvectors as the columns of your x, right? And then you see that x inverse ax is going to be what?
Your eigenvalues on the diagonal.
Yes, which eigenvalues? So is it?
Oh,
1, 2.
1, 2.
1, 2. Right. If I had done it in the opposite order, then it would have been 2, 1. Okay. So there's some, leeway, there's some flexibility here, right? Because you don't know what order you done it. Yeah, Tara.
This may be a really stupid question, but
That's
why
it.
is it negative 1, 2 and not 2, negative 1 for the spin of the null space?
Oh, you're right. Yeah, it's 2, negative 1. It was not a stupid question, on the contrary. It was a stupid mistake. There are a lot of mathematicians who can't do elementary arithmetic. Unfortunately, being unable to do elementary arithmetic doesn't make you a mathematician. I wish it did. Okay, everybody all right with how to do that? Right, it's simple, right? So, once you know how to do it, then you just find the characteristic polynomial, get the eigenvalue, get the eigenvectors, and then you're done. Okay. This might not always work, right? Not all matrices. It's not true that you can always find an eigenvector basis. We lucked out here because we're in R2 and we've got 2 eigenvalues, right? We've got 2 distinct eigenvalues, so we're guaranteed an eigenvector basis. But that's not always going to happen, right? That may not happen. It may not happen at all. So here's some definitions. One, if A does not have n linearly independent eigenvectors, we call it defective. It's like an insult, defective. Okay. But I have to say that I've never heard this term outside of this book. So the book calls them defective. Fine, whatever. It's not, in any case, it's not diagonalizable. Okay, not diagonalizable. Okay. Related to that, so you might be wondering when is a matrix diagonalizable and when is it not diagonalizable? When is it defective, right? There are 2 definitions related to that. say that lambda naught is an eigenvalue of A. In other words, a root of the characteristic polynomial. Okay. We call the degree of the root of lambda naught as a root the algebraic multiplicity of lambda naught. The algebraic multiplicity. Okay, so for example, over here, the algebraic multiplicity is 1 for each of these guys, right? Because they are single roots. They're not double roots, right? They're not triple roots, right? They are just plain old roots. Okay. So here, these guys have algebraic multiplicity 1 and 1, right? These two eigenvalues have algebraic multiplicity 1 and 1. Okay. Question number 3. We call, so this is sort of continuing, maybe I should put it like this. I'll put the 2 here, 3. We call the dimension of the eigenspace of lambda naught the geometric multiplicity. Of lambda naught. Okay. In our example, you see that the dimensions of the eigenspaces were 1 and 1, right? So in this case, we have the geometric multiplicity is also 1 and 1 in our example, right? Because the dimension of E1 was 1, the dimension of E2 was also 1. Okay. So here we have the geometric multiplicity equaling the algebraic multiplicities. Okay. What we'll see in 1 second is that the geometric multiplicity is always less than or equal to the algebraic multiplicity. The geometric multiplicity is always less than or equal to the algebraic multiplicity. The dimension of the eigenspace is always less than or equal to the degree of lambda naught as a root. Okay, so the only way one can have an eigenvector basis is if the geometric multiplicity equals the algebraic multiplicity for all eigenvalues. Right, because since the sum of the degrees of the roots of the characteristic polynomial is n. So, sorry, as usual, we have an n by n matrix. Right? You've got a degree n polynomial. The sum of the algebraic multiplicities is going to be n. Right? Because the sum of the degrees of the roots is going to be n. Right? Okay. So the only way you can get up to n is if the geometric multiplicities are are equal to the algebraic multiplicities, right? Because if any one is less than it, well, you don't have enough eigenvectors. You can't get n linearly independent eigenvectors. Okay. Okay, let me see if I can sketch out quickly why this proof is true. Okay. Proof of the theorem. Okay, do that first. Okay, so suppose that lambda naught is an eigenvalue with geometric multiplicity d. That's an eigenvalue, it's geometric multiplicity d. In other words, the dimension of the eigenspace is d. And we can find d linearly independent eigenvectors. Let's call them V1 to VD. Okay. And linearly independent eigenvectors. Extend them to a basis. Of Rn. Okay, so again, we have some n by n matrix. Extend them to a basis of Rn. So you can throw in some guys. D plus 1 to Vn. Okay, so you throw in these extra guys, but these guys aren't eigenvalues, aren't eigenvectors. They're not eigenvectors, or not necessarily eigenvectors. Okay. Well then, let's call that basis B. Okay. Then the matrix representation with respect to B and B, what's that going to look like? The matrix representation with respect to B and B.
It will be diagonal up until d plus 1, or v d plus 1 to vn.
Good, exactly. So it'll look like this. It'll be diagonal. Oops, forgot lambda naught. All these guys all have the same eigenvalue, lambda naught. So lambda naught. I can't say it quickly. Right? Be like this, and 0 down here, right? Right. You're going to have the multiples of the standard basis up until a certain point, and then after that, you don't know, right? Some other stuff. Okay. But up until that point, looks like a diagonal matrix. You're looking at the columns. Well, it looks good because we've got d eigenvectors, right? So this would be d. The first d columns are diagonal. Now, what's the characteristic polynomial? So this is going to be something like x inverse ax. Or maybe I should call it b inverse a. Well, anyway, x inverse ax. Now, what's the characteristic polynomial? X inverse ax minus lambda I. What's that going to look like? What's the characteristic polynomial going to look like? if this is the matrix, well, part of it you don't know, right? But part of it you do know. What's the part you do know? Oh, it'll be lambda naught minus lambda times lambda naught minus lambda times lambda naught times minus lambda d times. Right? So you're going to have lambda naught minus lambda to the d times some leftover stuff. Right? But what you do know is that your polynomial, maybe I should call this q, because I see some q first polynomial, right? What you do know is that the degree of lambda naught is at least d. Right? The degree of lambda naught is at least d, in other words, the geometric multiplicity. Of lambda naught.
Wouldn't that be the algebraic?
Exactly. Well, so I'm cheating you. Why am I cheating you? Why are we not done? We have the determinant of this minus this equals this times some polynomial, right? So the degree of lambda naught as a root is greater than or equal to the geometric multiplicity of of lambda naught. Why are we not done? Why have I sort of cheated you?
Because isn't that already
This isn't the characteristic polynomial of A. This is the characteristic polynomial of x inverse AX. Right? So I've got the degree of this guy as a root of the wrong characteristic polynomial is bigger than this. Okay, but it's okay. Don't worry. Right? This is the same thing as x inverse A minus lambda I x. Right? You guys see that? If you multiply this thing out, this is what you get down here. Right? Because you get, right, x inverse A minus lambda I x is the same thing as x inverse AX minus x inverse lambda I x. But this is I, so the x and the x inverse will cancel each other out. Right? So this is the same thing as x inverse AX minus lambda I. Okay. And then we say, well, the determinant of a product is the product of the determinants, right? But the determinant of x inverse and the determinant of x multiplied are reciprocals, right? So that's just one. And so we end up with actually the characteristic polynomial. Okay, so the characteristic polynomial of the similar matrix is the same thing as the characteristic polynomial of the original matrix. Okay, so it was actually not wrong. I haven't cheated you. So this guy, the degree of lambda naught as a root of the characteristic polynomial of A is greater than or equal to the geometric multiplicity. In other words, the algebraic multiplicity, i.e. the algebraic multiplicity must be greater than or equal to the geometric multiplicity. Okay. And I'm sorry to do this, but it'll only take half a minute more. Here's an example. If you look at this matrix, 102, the characteristic polynomial looks like 2 minus lambda squared 4 minus lambda. Okay. So 2 has algebraic multiplicity 2. But if you look at the null space of A minus 2I, this thing has a one-dimensional null space. That is, the geometric multiplicity is smaller than the algebraic multiplicity, right? And so, so the matrix is defective. You can't diagonalize it. It's not diagonalizable. If you go on and take more linear algebra, you'll see that all matrices are almost diagonalizable. Okay. That is, there's always a basis that will give you the eigenvectors, eigenvalues down the diagonal, but there might be occasionally like ones underneath it, so like almost diagonalizable. This is called the Jordan canonical form. Okay, sorry to keep you over. That's it for today.